All right, in this video, we're going to look at center of mass in two dimensions. So imagine you have a thin metal plate that occupies a region R in the XY plane. And one way to think about the center of mass for this plate is to imagine you have a pen with a sharp point, and we're going to look for this special point on our plate such that if I were to rest that plate on the pen tip, the plate would balance. And we'll label that special location as X bar, Y bar, and this will be referred to as the center of mass for the plate. And while this is a perfectly good intuitive interpretation for center of mass, as we'll see in the next couple examples, it is possible for the center of mass point to actually lie outside the region, in which case this interpretation would have to be modified appropriately. Okay, so as we saw in the one-dimensional case, another way to think about center of mass is in terms of moments. And now that we have two spatial coordinates, an x and a y coordinate, we're in turn going to consider two different moments. Okay, so let's first imagine just subdividing the plate into a bunch of small little rectangles. And as long as these rectangles are sufficiently small, we can think about the mass of this little rectangular portion of the plate as being concentrated at a point inside that rectangle. And we'll label that point xi star, yj star. Okay, so now, just as we did for the one-dimensional case, I can think about computing the moment of this point about the y-axis as well as the moment of this point about the x-axis. Okay, so first note that the mass of this rectangle can be approximated by taking our mass density function that we'll call rho and evaluating it at this sample point, xi star, yj star. And if I take that mass density and multiply that by the area of this little rectangle, so delta A, that in turn will give us at least an approximation to the mass of the rectangle. Then we can go ahead and compute what we'll call the moment of this rectangle about the y-axis. And so to do that, what are we going to do? Well, we're going to take the mass of the rectangle, which is just this right up here in blue, it's just rho times delta A. And then we want to multiply the mass by the distance of this rectangle to the y-axis. And what is that distance? Well, that will be simply the x-coordinate of this location, right? At least approximately. Okay, so likewise, we can measure the moment about the x-axis. That's going to be our mass times the distance of this rectangle to the x-axis, and that is going to be given by the y-coordinate. Okay, so then what are we going to do? Well, these are just the individual moments. So now if I go ahead and consider the moments of all these little rectangles we're going to get through our partition and then sum them up, those are going to give us in turn the total moments about the y-axis and the x-axis. And then we're going to take an appropriate limit, and that's going to lead us to these following integrals. Okay, so first the total mass of our plate, that's going to just be the double integral of rho dA, right? That just comes from this observation up here. And we've done this kind of calculation now quite a bit in this chapter. Then what we'll call the total moment about the y-axis, we'll label that as my. And this is going to be the, well, sum of all of these individual moments of these little rectangles about the y-axis. And then by taking the limit there, we're going to just take the individual moments and sum them as we vary over our plate. Okay, and so that's going to give us a measure of the tendency for the whole plate to rotate about the y-axis. Okay, and then likewise for the moment about the x-axis, that's going to give us a measurement of the tendency for the whole plate to rotate about the x-axis. And be a little bit careful here. This can get a bit confusing. Okay, moment about the y-axis, so my, but notice in the integrand you see x times rho, right? So again, the thing you got to keep in mind there, the reason why we see x is that x really is the measurement um, of the distance between our location and the y-axis. Okay, and likewise here for the x-axis moment, you see the y show up in its integrand, and that's because the y coordinate is the measurement of the distance between the location and the x-axis. So you got to be very, very careful there. Okay. Now to measure the center of mass, okay, just as we did in the one-dimensional case, we'll now take, say, for the x-coordinate of the center mass, we're going to take the total moment about the y-axis and then divide that by the total mass of the plate. And then to find the y-coordinate of the center of mass, we'll take the moment about the x-axis and divide it by the total mass. Okay, so this location here, we can now think about as if we were to take the entire mass of the plate and concentrate it at this center of mass point, the x bar, y bar. Okay, then the rotational tendency for that new point mass about the y-axis and about the x-axis would be the same as the entire plate itself. All right, so in the next video, we'll go ahead and work through question 2, illustrating some computations here. So I'll see you there. Thanks.